everybody. So when we left off, we were talking about how, and my head's cut off, but you need to be able to see my table. So we were talking about how we remembered with this brass ball, remember when it's cold, it fits through, right? Kind of a tight fit, but it fits. And then when we heat it up, what happens to the molecules when we heat them up?
They spread apart.
They spread apart. Why do they spread apart?
Because they have more energy.
They have more energy and they're moving faster. Are they still tightly bound together?
Yes.
Still very tightly bound together, but they spread apart a little bit because they have a little bit more energy. And we're heating it up and we're heating it up. Did I heat it up enough? Let's see. And it's too big to fit through the ring. Okay. So the question was water. So we know that water, when it freezes, it forms a crystal and it grows. The question is, when water heats up, does it expand like our brass ball does? And some of you said yes. And some of you said no. And those of you who said no were like, we're no, but we're wishy-washy about it, right? So what did we decide to have as a test? You guys remember? Mason. Put hot water over cold water and see if they mix. So guess what we're gonna do?
Put hot water over cold water and see if they mix.
We're gonna put hot water over cold water. We're gonna see if they mix. So I have, can everybody see? I have baby food containers, okay? And I am gonna fill them completely full of water. The blue is gonna have very cold water in it. It's ice water. So what temperature is it? 0. Oh, it's green.
Why is it green?
Because I dyed it green.
Oh.
I have some food coloring at the bottom that I actually put there last night. It's gonna take a little bit because it dried up. Not last night.
You're like, it's magic.
It's
But
magical!
it's like good magic. So.
Oh wow, it is cold. And I'm gonna pour it like really all the way full to the top. Okay, woo!
Whoa.
So full, we're gonna spill a little bit. Okay, then the red is gonna be hot water.
Doing Christmas colors.
I'm doing Christmas colors, not intentionally, just because they have good contrast. They're on opposite sides of the color spectrum. So this one's dissolving way better because it's hot. So hot water, clear all the way to the top. Okay. Okay. So we're gonna get the hot water on top of the cold water. So I'm gonna do that with a piece of plastic. I'm gonna flip it over like this. Okay. And put it on top of the cold water, and oh my, it is warm. Okay, now.
Use a table trick thing.
Yeah, but really slowly, actually. It's not really the table trick thing. Come on, Debbie. You can do this. Woo! Did I mention it's warm?
No.
I mentioned it's hot.
Okay.
That's like when I try to take
I'm just going to have a moment with my fingers.
I've done it once before. It's so hard.
Okay.
The Indiana Jones.
Moment of truth, people.
Oh. Gonna fall over.
Shouldn't get tired.
Oh.
That's
Oh, wow.
Water slightly less dense.
But I know the hot water is heavier.
Why would the hot water be heavier?
Electrons don't count.
But it doesn't even have more electrons. The molecules are all the same, but they are more spread out than, oh guys, this is perfect.
So there's technically more cold water there than hot water.
Technically, there's a few more cold water atoms, yes, or molecules,
Yeah.
because they have the same volume. Yes. Actually, and do you remember, remember when we were doing the condensation?
Mhm.
Oh, we have Sophie. awesomeness, but we have Sophie. Sophie, you missed some awesomeness. You're gonna have to go back and watch the recording. But we have some hot water on top of some cold water, and they are not mixing. So what'll happen, actually, you guys remember when we were doing the condensation, some of you got a really, really, really tight seal, and your cup started to collapse. Do you remember that?
Yeah.
What was happening is you had, I'm going to draw a picture. So air pressure is going to be equalized, okay? So you had your cup and it was upside down like this, and it had a bunch of hot air molecules in it, right? And they were pushing out on the sides of the cup with the same force that the air on the outside was pushing in. And we know that because it wasn't bulging and it wasn't collapsed, okay? But then they cooled down. And they became less dense because they cooled down. And because they had less energy, they weren't pushing as hard on the sides. They were still pushing, just not as hard. So now the air on the outside was pushing harder and your cups caved in. Because there was more air on the outside that was pushing in harder because this cooled down. It's the coolest thing in the world. I love it. So because you have fewer air molecules in there because they were hotter when you closed it in. Same thing will happen. Like I will, we'll put leftovers in the away, right? Like we have dinner and dinner's hot. We put it in a Tupperware. That air above my leftover spaghetti is hot, right? Because my spaghetti was hot, and I put the Tupperware in, and then I put it in the fridge or the freezer, and it'll like suck in because those air molecules, they slow down, they cool down, and they take up less space because now they're smaller, and now I've got a vacuum in there, and it's really pretty cool. So that's what happens with the cold water and the hot water. What if the cold water was on top? They would mix. Now, I want to show you guys something. This is room temperature. I've got to angle this down again. So this is just scary. This whole hot water, cold water thing is, but it's so perfect. You guys are going to have to come and look at it up close. Okay. So these are both room temperature water. Okay. Completely room temperature. They've been sitting there since like last night. And this is highly concentrated blue water that I'm going to put at the very, 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 very bottom. Okay. I got a little bit at the top, but I'm mostly just putting it at the bottom. Okay. I sucked in some water in there.
Yeah.
Okay. So I'm going to put some at the very, very bottom. So it's very concentrated blue at the bottom. Okay. So in nature, these are the sediments at the bottom of a lake. Okay. And what happens is you get ice at the top of a lake. Right? Oh crap, I have a big globby of ice. Oh, there we go. And what will happen is the ice will melt at the top of the lake every spring, right? I'm going to have the one on the left be our ice. So this is the ice at the top of the lake. And it's going to start to melt. Holy smokes, this water is cold, people. In case you were wondering. Okay, so the ice is going to start to melt. And do you see what's happening with the blue in the water? It starts to mix. Like if you look, you can see it. You guys need to come up and see this too.
Yeah, it's like coming up.
It's like being sucked up from the bottom. And what's happening, the ice is floating because it's got its crystal matrix, and so it's way less dense than water. But as soon as it melts, that water is as cold as it gets, and it's going to be more dense than the water, and it's going to sink. So it sinks, and it stirs up the stuff at the bottom, and the stuff at the bottom is going to come up, and it's going to churn the water. This is what keeps our lakes alive. So you've got all this fish poop, all this stuff at the bottom, right? Nutrients for the lake, things for the fish to eat, things for the plants to eat, things for everybody to eat. It's all stuck at the bottom. When the ice melts in the spring, it stirs the lake, gets everything going, and gets those nutrients flowing in the lake. So I'm going to end the video. That's what you guys needed to see, but isn't that so cool? There are some experiments for you guys to do with hot water and cold water. Costin and Sophie, I think you guys are both doing those at home. But you can totally see this is being stirred, and this one's kind of just, it's stirring a little bit because you've got that random motion of the molecules. The molecules are going to move anyway, but they're going to stir more if you don't have it. Guys feeling good, Costin and Sophie?
Yeah.